Hello everyone and welcome to another video. Today I would like to talk about one of the most famous partial differential equations around, the one-dimensional wave equation. The focus of the video today is actually just on deriving the equation here. We're going to leave the solution of this equation to another video. And while this video here is designed to stand on its own, I do want to mention that this is actually part of our multi-video series discussing partial differential equations. I'll leave a link in the description below to all of the other relevant videos in this series. So with that being said, why don't we jump in and talk about the 1D wave equation. Now, this shows up in a lot of different engineering and physics and science applications. And the picture that goes along with it, or at least one of the applications where I think is the easiest to physically understand where this equation comes from and what it describes here, is to consider the case of a string here. So let's just draw ourselves a string here. Maybe we'll draw it like such. I don't know, maybe it looks something like that here. It doesn't have to be sinusoidal here. It could be some odd deflection here, but maybe let's just draw, you know, an x-axis or something like this here. Like this. And what I want to talk about here is, let's talk about the deflection here away from the horizontal position. So you can imagine that maybe this is like a guitar string or something like that, where it would vibrate up and down sort of in this plane here, right? So maybe, you know, let's put this n here at 0 here, and maybe we'll say this thing has a length of L here. And what I would again like to say here is we want to measure what is the deflection. Let's call this just U here. Now, what makes this interesting is if you think about this long enough, the deflection of the string here, U, it's actually a function of many different, well, not many, but in this case, two independent variables. Namely, this thing is going to vibrate up and down here, so there's some time aspect here to it, right? And the other thing that's interesting is every position here of this string here has some x coordinate associated with it as well here, right? So in this case, what we're talking about here is I would like to find this function u here, which is a function of time and space x here. So in this case, with our guitar string or our vibrating string example, u of tx, this might represent the deflection of the string in the vertical direction. However, like we said earlier, this vertical direction here, this is at a given time t and given spatial location x, right? In other words, the horizontal position here. So that's what we're looking for here. To set the stage even further, or to help visualize this, now might be a great time actually to pause here and look at our other video that discusses standing waves. And we are going to actually do a little demonstration showing how this rope might deflect and some of the interesting behavior and modes that come out of it here. So what we want to do now is derive the equation of motion, which governs how does this string vibrate up and down here in this scenario. So the way we want to do this is, let's approach this and look at a small infinitesimal little gap here, or chunk of this string here, or this chord here. Let's pick 2 points. Let's call this maybe P and Q here. So P is located at a distance, let's call it X. And we're going to consider this point Q to be a distance delta X away. So this location here is obviously X plus delta X, right? And I think it might behoove us to actually zoom in on this scenario, or this little small chunk here, and draw it a little bit larger. So let's do that over here. Let's redraw the picture here, but only focus on the points P and Q here. So what I'm going to do is, again, we'll draw this in an exaggerated fashion. Let's have P here. Let's say you got the string doing something like this maybe, and then you got Q over here. Okay, again, we said P is located at a spatial location X, and Q is located at a spatial location X plus delta X here. Okay, so that's the physical setup. Let's make a couple of simplifying assumptions for this. So in terms of assumptions here, we're going to make a couple of them. One here. let's assume that the mass of this string is uniformly distributed across the entire length of the string here. So let's just write this down and say, how about that the mass per unit length, you know, this is in units of kilograms per meter here, is constant. So there aren't any lumps or knots or super dense sections of this string. It's basically the same density across. And again, let's make a note here that we're going to be using units of rho here, right? And rho is going to be in we're going to be using a variable of rho to denote the linear density here in units of kilograms per meter here, right? So if you buy yourself a 1 meter long rope here, it's and the density here is 0.5 kilograms per meter. That whole rope is going to weigh half a kilogram, but that half kilogram of that mass is evenly distributed over the entire length of the string here, right? So that's our first assumption. Let's go ahead and write down a second assumption here. All right, sorry, I'm back. My laptop ran out of batteries here. So let's come back here to our assumptions here. The second assumption here that we'd like to make here is that we want to assume here that the string is perfectly elastic here. So let's write that down. So string is perfectly elastic and offers no resistance to bending. Right? So in other words, the picture that goes along with this, right, is we're looking for, you know, a string like we looked at in that standing waves demonstration where, you know, it's very easy to deflect here. It's got no ability to resist a moment in bending here. So we're not dealing with something like, you know, a string of plastic pens here, which you know, if you try to bend this thing, it doesn't want to really vibrate very well because there's got some resistance to bend it. Whoa, crud. Yeah, well, as you can see why, that's not going to work for our PDE here. So let's just go with assumption number 2 here. String is perfectly elastic and has no resistance to bending here. How about number 3 here? Let's say that the gravitational force on the string is negligible. So let's say gravity or gravitational force is negligible. And that's pretty reasonable if you think about this long enough here, because we're going to have a string which is stretched nice and tight here, and the tension in the string is actually going to be the dominating force. And the gravity acting on this little bit of string here really should not influence it. If you have a problem with this assumption here, maybe just think about taking this string and instead of having it oscillating vertically, just turn it 90 degrees so it's oscillating in a plane that's perpendicular to gravity. So again, gravity here won't play much of a role here. Okay. How about assumption number 4 here? Let's assume that the string performs small or none, small / negligible transverse deflections. So in other words, this is in the x direction. So another way to think about this is it's really the only motion that's happening with this string is that it's going up and down. Sure, this tiny little bit here as it moves up and down, it might go left and right a tiny little bit, but that's going to be negligible compared to the other motions here of the string. So again, assumption number 4 is I don't think it's going to be breaking anything too badly. So number 5 here, let's make our last assumption here and then we can get down to this here. Let's assume that the slope of this string is small at all times here. So in other words, the vertical deflections are small enough here. Let's write this down. So vertical deflections, aka in the u direction, are small at all times, and therefore slopes are small. So in other words, coming back to our little rope here, right? If you stretch this thing nice and tight, and if this thing is vibrating up and down in the string in the plane, right? It really is not vibrating a lot up and down. So we're not going to consider cases like this, right, where you've got this huge giant bend here, and now the slopes are definitely not small along this string here. So instead we're going to look at cases where, yeah, this is fairly tight and it moves up and down here, but the slope at any given location here is small. Okay, so great. With that, I think that's a reasonable set of assumptions here. I think we can go ahead and take this and start trying to turn this here into a partial differential equation here. So again, maybe what we should do here is let's erase this half of the board. We'll leave our picture here up because we're going to be adding to that in a second. Okay, so let's write this down here. So let's go ahead and talk about the derivation of the 1D wave equation. Okay, so the picture that goes along with this here. So let's go ahead and add some forces to this picture here. So again, we said this is that small little infinitesimal chunk here of string here. And let's assume that maybe on the left side there's a tension T1 on the string, and it's going to act in the direction of the string here at location P. So maybe what we can do is we can draw that like this. Let's call this tension T1. Similarly, on the right side of the string, we're going to have a tension T2, which acts in its direction here, aligned with the string. Let's call this thing T2, right? Perfect. And what we can do now here is let's go ahead and also look at the angle that this force makes with the horizontal. So we see, let's call this alpha, this angle alpha, and then similarly over here on the other side, let's call this angle beta. Okay. All right. So if we do that here, what we can do is let's go over here and write down what are some of the consequences. So namely, let's look at how about consequence number 4 here. So if in order for assumption 4 to be true, we see that the horizontal components of these forces have to equal each other, right? So let's write this down. For assumption A3 to hold, right, we need the horizontal components of force to be equal. So let's just write down what are the horizontal components of the force. So on the left hand side over here, we see that the horizontal component, it's what? It's T1 cosine alpha, right? So I have the left side force is T1 cosine alpha, right? And that better equal the horizontal force on the right side, which we see is T2 cosine beta. All right, boys, sorry, I'm not having good luck with technical issues today. So now the camera ran out of batteries halfway through that. So I went through and then realized something was wrong, but I think I backed up and got us back to this exact same location. So like we were talking about earlier, we said that in order for assumption A3 to hold, mainly that the thing doesn't move in the transverse direction, the horizontal components had to equal each other here, right? Now, remember one of our other assumptions, I believe A5, which unfortunately I erased, but hopefully you have in your notes here, is that the slopes were all small. So namely alpha and beta were small everywhere here, right? So if alpha and beta are small here, cosine of something small is basically 1, right? So we see that what this ends up with is that T1 and T2 are basically equal to the same tension here. So there's one tension through the string here. And what I can write here is this is just equal to T here, right? So everything's the same. This cosine of something small and cosine of something small really is not going to matter here. So we end up with this relationship here. So let's box this up here because we're going to use this in a second here. So this is also the same, basically saying that the horizontal components are all equal here, right? Okay, so how about the vertical direction here? So hopefully there's some motion in the vertical direction, right? That's the whole point of having this string move here. So let's talk about, how about thinking about this string chunk here as like a very, very small mass, which is moving in the vertical direction. Well, here on Earth, apparently, I think this guy Newton came up with this second law here, which tells you how things move around here on Earth in an inertial frame. Isn't that something like some of the forces in the vertical direction is equal to the mass of this thing times the acceleration in the vertical direction, right? Okay, so all we have to do is start adding this up. So first of all, let's go and get the forces in the vertical direction. So looking at our picture here, we see the vertical forces are basically what? It's T2 sine beta minus t1 sine alpha, right? So we end up with here, t2 sine beta, right, minus t1 sine alpha, right, is equal to the mass times the acceleration in the vertical direction. Now, acceleration, I think you'll remember from high school physics, acceleration is the second derivative of position here, right? Well, what's the position of this little mass of string? That's u here, right? So in other words, I can say that the acceleration in the vertical direction, it's the second partial of u with respect to time, right? Here is acceleration in the vertical direction here, right? Great. Okay, how about, oh, sorry, maybe what we should have done is we should have figured out mass here. The mass here, another way to describe the total mass of that little chunk here, right, it's rho times the distance of the string here, right, which we said was delta x, right? The string is delta x long in this little chunk here, so rho times delta x. Okay, great, I think we're all consistent now. All right, next step here is let's go ahead and divide both sides by t here. So let's divide this thing by t, divide this by t here, and maybe we'll rewrite it over there. Give me a second, sorry. All right, so now if we divide this by t here, what we can do here is let's rewrite this whole system here as, I'll come over here. Maybe now this is a better spot here. So left-hand side, I could rewrite this thing as t2 sine beta minus t1 sine alpha. This is divided by t here. This is divided by t is equal to rho delta x over t times partial u squared with respect to t squared. Okay, great. Now let's make a note here. So if you recall, previously here, the thing that we boxed up earlier, t here was just cosine 1, or t1 cosine alpha, t2 cosine beta, and t, that's all the same thing. So tell you what, how about for this t, let's write this as t2 cosine beta, and for this t, let's write this as t1 cosine alpha. In other words, this left side could be, let's do this for one first here. So now this here, this t, I want to replace this with t2 cosine beta here, right? Minus t1 sine alpha. And then for this t, I want to replace it with t1 cosine alpha. So this is t1 cosine alpha, right? Is equal to same thing on the left-hand side. Let's not deal with that yet. Dot, dot, dot. Same thing. Okay, now this is great. The t's cancel here. And if you remember, what's sine over cosine? Isn't that just tangent here? So I can write this whole thing here as tangent beta, right, minus tangent alpha is equal to this thing over here. Again, let's make a dot, 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 right? It's the same thing carried all the way down. Now, let's look a little bit more closely at this term tangent beta and tangent alpha. Let's look at tangent beta first. If you look at this thing long enough, the picture over here, you see, where is tangent beta? Tangent is, if you remember, tangent is what it's opposite over adjacent, I think. So it's opposite, like say like this height here. Here's your opposite if you want to think about it in this kind of shooting from the hip method here, right? Here's the adjacent here. So actually, tangent of beta is the same thing as the slope of this thing right here, right? So that's basically giving you the slope of this red arrow here. In other words, it's giving you the slope of the string here at x plus delta x, right? So maybe let's be very explicit here and write this down here. So we see that tangent beta, right? This is slope of string at x plus delta x, right? What's another way to describe the slope of the string here, right? Isn't that the same thing as the partial of u with respect to x here at x plus delta x? That's like another way to explain it here, right? And by that exact same logic, you can do the same analysis for tangent alpha. So tangent alpha over here, opposite over adjacent, or rise over run, it's basically saying tangent alpha is the slope of the string here at location x here. So let's write that down here. So tangent alpha is basically partial u with respect to x at x, right? That's the other way you could look at this. Okay, great. So replacing that into our expression, let's go ahead and erase some of this. Let's see where we end up now. Okay, so we said tangent beta here. What we could say is we can write this thing as partial u with respect to x at x plus delta x, right? Okay, minus partial u with respect to x evaluated at x here, right? So again, I don't mean to belabor the point here, but I want to make sure we're on the same page here, right? This is the same thing as tangent beta. This is the same thing as tangent alpha here. Okay, this is the left-hand side here is now equal to, now's maybe a good time to rewrite this thing here. It's rho delta x over t times partial u with respect to t squared, right? Okay, let's divide through by delta x. Move that to the other side. So I can write this whole thing as, maybe let's write this as brackets here, is 1 over delta x. Here, and then here we got partial u with respect to x, evaluated at x plus delta x, minus partial u with respect to x at location x here, is equal to rho over t partial u with respect to t squared. Right? Okay, let's look at this again here. Let's look at this term in brackets here, right? And look at it in conjunction with the picture over here. What is this asking? This term here, this here is the slope over here at point Q. This here is the slope at point P. The difference here between these two is basically how much did the slope change here, right? So if you want to write this down in some English interpretation, this is how much did slope, in other words, partial u with respect to x here, right? Again, we've got to be careful when we say slope. I mean physical slope, the deflection with respect to changing the position. How much did the slope change between point P and Q, right? You can think of that almost like a rise here, right? Because if you look at this, there's this term over here, delta x. What is delta x? Delta x is literally like the run of how far is point P and point Q different from each other, right? So if you think about this long enough here, if we take the extension here of delta x, think about this as delta x gets really, really small here, right? What is this whole left-hand side? The left-hand side is asking how much did the slope change as x changed, right? In other words, it's asking about the rate of change of the slope, or this whole left side is basically what? It's the second derivative of u with respect to x, right? If we take the limit as delta x gets small here, right? So this whole left side boils down to, you tell you what, let's come over here and erase this and write it down with a little bit more clear board space, because I think we're getting really close here, right? So the left-hand side becomes basically partial u with respect to x squared here, right? So again, let's make sure we're all on the same page here, right? The term in brackets is how much did the slope change, and the denominator is how far in the x direction did you move here. So again, yeah, that seems reasonable. That is the second derivative of u with respect to x, or the second derivative of position with respect to x here, right? Or you can think of it as the first, never mind, I don't want to, yeah, I'm belaboring the point here, right? Okay, so great, we got the left-hand side, and now the right-hand side, it's just rho over t times partial u with respect to t squared. Great. All right, and you know what? Rearranging terms, what usually happens here is people want to solve for the derivative with respect to time, is how you'll typically see this equation presented. So let's just move these constants to the other side and solve for partial u with respect to t squared. So I get partial u with respect to t squared is just equal to tension over linear density here times partial u with respect to x squared. Great. And typically what you'll see here is, this is just some mishmash of constants. It's tension over density. However, in this case, and in most cases for the 1D wave equation, right, this is a constant number, right? It doesn't make any sense to have like a negative tension here, and doesn't make any sense to have a negative density here. So usually to denote that this coefficient has to be positive, what you'll typically see people write here is, this is partial u with respect to t squared is equal to c squared partial u with respect to x squared. So again, this is the more common representation here of the 1D wave equation here. So this is 1D wave equation. Okay, and all this c squared constant is denoting here is it's trying to tell you that this coefficient is usually positive, a la something like tension over density here, right? So here we are. This is our 1D wave equation here. And this is the governing partial differential equation. And if you look at this thing long enough, you see that what? It's a second order partial differential equation. It's linear, it's homogeneous here. So there's a lot of tools that we can go forward with trying to solve this here. However, that's the topic of another video here. So I think we've gone ahead and successfully derived the 1D wave equation here. So if you enjoyed the video, please subscribe to the channel, because we're going to have another video coming up which discusses actually how do you go about solving this here, and talking about other engineering topics as well. So with that being said, I hope to catch you at a future video. Bye!